Welcome. This time I want to look at vorticity and try to give some idea of what it physically means and how it's used and some of the properties it has, particularly in two-dimensional flow. So in a previous lecture we looked at irrotational flow and saw that if you have irrotational flow then you can derive useful quantities such as the flow potential, and you can derive things like the Bernoulli equation, which allow you to perform simple calculations for things like aerofoils and useful things like that. So if we have irrotational flow, we had this curl of u is equal to 0. What I want to do in this lecture is look at what happens when this is not 0, and so we define a quantity omega, which is going to be the vorticity, this curl of u. And this is the vorticity of the fluid. So try and give some idea of what this is. This is a rotation, some kind of twist of the field of the flow field, and it's a local rotation. I'll try and give some examples to show what I mean by that. So one is if we have a flat plate, for example, like this. So we have just a flat plate, and we have a flow in this direction, and it has some variation. So it has say a slow speed here and an increasingly large speed as we go this way. So we have a flow which is changing. It's not obviously rotating, it just keeps going forever. So you can imagine this as a very long kind of plate. But if you have a flow which is in the x direction, so u is just in the x direction, we can say that here this is some quantity times y. So the flow in the x direction but depends on y with some constant at the front. And it's not flowing in y and not flowing in z, so it's just only in the x direction. Okay, so then we work out what vorticity is by working out the curl of this expression. So omega x is it's du z by dy minus du y by dz. Omega y is du x by dz minus du z by dx. And an easy way of doing this is once you've got one of them, you just cycle. So y becomes z, z becomes x, x becomes y, and you just cycle them around. And so here just have omega z, so y just becomes z, du y by dx. Now here we have du x by dy. Okay, so we work out what these are. So here uz is 0, and uy equals 0. So here these two are 0, so this whole thing is equal to 0. Uy, well ux is not 0, but there's not varying in z. So into the page there's no variation. So this part is equal to 0, and uz is equal to 0. So uz here ux doesn't depend on z here. And so again, this whole thing is equal to 0. And then finally, here what we have is, so uy is equal to 0, so that part disappears. And so we just have dux by dy, which is this beta term, which is minus beta. And so here we have vorticity. So vorticity is not equal to 0. In fact, there's vorticity into the page, but we don't have any obvious rotation. So no clear rotation. But we have vorticity. So essentially, it's the shearing of the fluid flow like this, which is the vorticity, not necessarily the rotation. So we show this in a few different ways. So we can imagine cases where we have flow in a circle. So I'll get a bit more space over here. So let's see, we have say flow just going around in a circle around some central point. And so we have here a flow going around, One way of visualizing vorticity is to imagine you have two matchsticks crossed. So you have at this point here we put, say, a matchstick like this and a matchstick crossed like this. I mean, imagine what happens when as the fluid moves. So as it moves around here, let's see, the fluid is carried around with the flow. If there's no vorticity, the fluid isn't rotated locally, and so the fluid is just carried, and the matchstick is not rotated. And so as you flow around here, essentially the matchstick moves like this, and the whole thing just moves around the circle. This is the case with no vorticity. So in this case there would be a vorticity at the very origin here, but in this region here where the fluid is, or where we're drawing the fluid, there's no vorticity. Conversely, you have a flow like this, so again, around in a circle, where you have a flow velocity again, so it's also rotating around in a circle, except now we'll draw this. So if we have rotation, then this fluid might now move like this. So we now rotate the fluid, and this is with vorticity. And so examples where you might have this occur is if you had if the velocity u theta, so if theta is the angle here, and you have some kind of u theta going around here. In this case, this might be proportional to the radius r, where r is going out here. This is r. In that case, like a solid body rotation, the fluid elements are being rotated as they move around the origin, and you have vorticity. In this case, you might have u theta, say, proportional to 1 over r. And in that case, it just moves the fluid elements, but doesn't rotate them. So hopefully that gives a little more idea of what vorticity is. So it's a local rotation of the fluid elements, but it's not directly linked to overall net rotation. So now I want to try and look at how this vorticity behaves. So what's the equation for vorticity? So vorticity equation. And so here we're going to start with the momentum equation. So start with the same equation as always, and this minus p. And if you remember, we can essentially replace this with a vector identity, and this becomes du by dt. So now I have a curl of u cos u. So this is a row in this point here. And now on this side, if we assume incompressible, then we can essentially move the density inside here, because the density is nearly constant if it's incompressible. And then we have a p over rho. And then the other part of this becomes half u squared. And so this is a vector identity. If not sure about this, see the previous lecture where I went through this in a bit more detail. Okay, so from this we can then essentially work out what the curl of this equation is. So if we take the curl, we'll get the curl of u in here, and so we'll work out the time derivative of the equations. So here we can write this is omega. So we can take curl of this equation, and a nice thing about this is that the curl of the gradient is identically 0, and so the whole right hand side vanishes. So note, so the curl of a gradient is 0, and so we just write so d by dt of the curl of u, which is the vorticity, plus the curl of this, which is the curl of vorticity cross u, equals 0. And so that gives us an equation for the evolution of vorticity in the incompressible limit. So this is an incompressible ideal fluid. So there's no dissipation, and the fluid's incompressible. We can then play around with this a little bit more and use some vector identities to expand this quantity here. So we can write this as d by dt. So this is a vector is a vector. So this is so you can expand it as a u dot grad omega minus omega dot grad u. And then we have the compression terms, so we have an omega times a divergence of u minus a u times divergence of vorticity. And now this whole thing is obviously equal 0, it's the right hand side. Okay, so there's a few things we can cancel out here. So one is vorticity is a curl, and so divergence of a curl is identically 0. So this is the divergence of a curl of something is 0. Here we're assuming incompressible, so this term also goes to 0. And so we're just left with these terms here. So we have that d omega by dt plus u dot grad omega. And now it's starting to look a bit like the other advection equations in Euler's equations. So this is omega dot grad u. And this is also quite a useful form. The last special case I want to look at is a case where you have two-dimensional flow. So it's useful in many cases where we can simplify a 3D system to just varying in 2 dimensions. So in tokamaks and plasmas, this is quite often done perpendicular to the magnetic fields, for example. In aerodynamics, this is often done for long wings. So if you just have a wing which has kind of a shape like this, assume that in this 2 directions, so this might be y and x, we assume that there's no flow and everything is constant in and out of the page. And so we can treat this as a 2-dimensional system. And so what we quite often want to do is make the assumption, so 2D of a 2D system. So assuming that this is just a slice through a very long, very thin wing. And so here you might have the z direction, but assume the flow is going over the wings, for example, but that nothing is changing in the z direction. And this allows us to simplify. So say d by dz equals 0, and say uz equals 0. So the velocity in the z direction goes to 0. And in this case, this simplifies this vorticity considerably, because if we go back to the definition of the vorticity components, what you can see is in here. So this is the components of the curl. So if we're assuming that uz is 0 and d by dz is 0, then omega x goes to 0. Same reason omega y also goes to 0, so uz is 0 and d by dz is 0. So all these components of omega of the vorticity goes to 0, and the only one that's left is the z component. And so omega only has a z component. So in 2D systems, so omega x and omega y are 0, and so omega is just omega z in the z direction, so unit vector in z. And this means we can put this into this equation. And so for the vorticity equation, we just have an equation for uz. So we just take the z component of this. And now the interesting point is this last term here. So we have omega dot grad u. So omega dot grad u. So that term, so omega is just in z. So this is just omega z. Then d by dz. D by dz of u. we already said that d by z is 0, so this whole thing is just equal to 0. So in the two-dimensional case, this right-hand side goes to 0, and we just have an equation just for the z component of omega. And so the equation just reads that d omega by dt plus u dot grad of omega equals 0. So this is in 2D, so ideal incompressible flow. The vorticity is constant along the flow. And this, in some ways, justifies the choices that led to the binary equation. So if you have flow along, say, along a wing, then what happens is, if the vorticity is 0, when this air is coming in and passing over the top of the wing, if the vorticity is 0, so you have a stationary fluid coming in here, as this fluid particle moves along this path here, if omega is 0 here, then it's still 0 over here. And so you can make this assumption of irrotational flow for fluid that's just being deflected over the tops of wings. And so you can use the unsteady or the steady binary equation. The exception is if you have fluid which is close to surfaces, where viscosity effects become important, and these assumptions break down. Or if you have three-dimensional flows, then this can also introduce vorticity as well, sort of twist to the fluid. But for many cases, zero vorticity or fixed vorticity are good approximations. These are useful enough to derive many useful results in aerodynamics. Thank you very much. See you next time.